Okay, so now we're at lesson 16.4, and we've been going through module 16, investigating how we use exponential models, right? So in module 14, in module 13, I think we encountered geometric sequences. Then in 14, we started dealing with exponential functions, which are like an expression of a geometric progression. And now we're using geometric progressions, exponential functions, to model data, right? So now, in this last lesson of Module 16, we are looking at comparing exponential models with linear models. Now, linear models drags up stuff we've done before that you've been encountering for a long time in your algebra and pre-algebra career. It's a line. And we can, as you know, we can also model data with a line. We call that a linear model, right? So it's a linear function that maps data. And now we've been using exponential functions, exponential models to map data, and those are curves, right? So what we want to do in this lesson is understand the differences and similarities between linear and exponential models, and we want to be able to tell the difference between when to use a linear model and an exponential model. So we're going to be looking at particular situations, and you'll need to be able to say whether that situation is best modeled by a linear model or an exponential model. And then you'll need to be able to write the equation and tell whether it's increasing or decreasing. Okay, so this lesson is another lesson where the book introduces a bunch of stuff you can do with computers or graphing calculators. They use regressions and tracing functions to have you do some computation. We're just going to do one piece of this lesson. I just want you to understand how to look at a situation and decide whether it's best fit by a linear model or an exponential model and be able to write the equation. Okay, so real quick, let's look again. Let's look for a moment at what we know about linear models and exponential models. Now, first of all, to remind you, they each have their own shape. Right? So if this is the Cartesian plane, okay, a linear model looks like a line, and an exponential model looks like a curve. Okay? A line or a curve. And a line and a curve. So we say the shape of a linear model is a line, and the shape of an exponential model is a curve. Okay? So that's a difference. And we'll talk about what that difference means here as we look over some other characteristics. Now this line says change per equal interval. So we're saying when your x changes by 1 at the beginning and when it changes by 1 a little bit later, how are those two vertical changes related? So you'll remember that in a linear function, in a linear model, on a line, no matter where I am on the line, the slope stays the same, right? The slope stays the same. So when my x goes from 1 to 2, if the line goes up by 3 over that interval, then later if I am on the interval 5 to 6, it still goes up by 3. So whether my interval is 1 unit here or 1 unit here, it still goes up by 3 in both places because the slope stays the same throughout. So we say that the change per equal interval, right here, the change per equal interval on a linear model is constant. Across the entire function, the change over a given interval, whether it be 1 or 2 or 5, if I can select a section of 5 at the beginning or at the end or on this side or on that side, that change of 5 will give me a corresponding change in height that stays the same across the whole function. Okay? So the change per equal interval is constant. Now what you'll notice here with our exponential models, in the beginning, my vertical change over a certain horizontal distance is very small. But as I go further along the function, the vertical change per horizontal distance increases. Okay? Because I'm multiplying every time, I'm multiplying one value by a certain number. As this value increases, multiplying by the same number makes a greater vertical increase the further out I go. So here we say that the change per equal interval is increasing. Increasing. Okay? So the change per equal interval, so if I select a section of from 1 to 6 at the beginning, a section of 5 at the beginning, it's going to change by a little bit. But if I go further out, and it's a change from 15 to 20, that vertical change along that 15 to 20 change in x, that vertical change is going to be greater than the vertical change was from 1 to 6. Okay? Cool. Now, the ratio over equal intervals. So if I take this value divided by the value before it over a particular interval, on a line, that number is going to decrease. So let's say the slope is 3, like we were talking about before, right? If I take the change and divide by the starting value over a certain interval at the beginning of the line, right? That change is 3, I divide by a small number, I get something. Now I come over here, I do the same thing on another interval as the values have increased. So I take now, the change is still 3, but now I'm dividing by a larger number to find the rate of increase, right? The rate of change. And so that ratio of one value to the next value decreases as those values get bigger, okay? So because the change itself stays constant, even as the values increase, the ratio over the equal interval decreases, okay? Decreases. However, because in the exponential function, the curve, right, the ratio stays constant. That's kind of how we build it. We're building it by saying I'm going to take this value, multiply by something to get the next value. Take this value, multiply something to get the next value. So that what I'm multiplying by stays the same throughout. So that's the ratio over the equal interval. It is constant. Okay. Now finally, so what we're seeing here is a linear model is an additive relationship. It's like an arithmetic progression. That's what we were saying in our recall, right? So when we're adding the same value again and again to move along the model, then we know it's linear, and it has these characteristics. If we're multiplying by something, it's a geometric progression, right? A geometric progression, that's an exponential function, that's an exponential model, and it has these characteristics, okay? So those functions that we've encountered now are, for a line, it's f of x equals a plus bx. And that b is your change, your slope, right? And the a is your starting value. And so, or if we're put it in arithmetic sequence terms, we would say the b is our common difference, and the a is our first term, right? So that common difference, that amount we're adding by to progress throughout the model, that's our b, okay? And we see the plus here. So if the common difference were negative, if we're actually subtracting 3 each time, our slope was negative, then it would be a minus 3x or something, right? But overall, it's an additive relationship, okay? And the function, the equation for an exponential function is f of x equals a times b to the x. And again, we've seen a couple of variations on this depending on what kind of model we're dealing with. But the core form, right, is a times b to the x, where a is our starting value and b is our ratio. So that's what we're multiplying by to progress through the model or through the function. And so it's a multiplicative geometric relationship. We're multiplying by something in an exponential equation or an exponential model. In a linear equation or linear model, we're adding something to move throughout the equation, okay, throughout the function. So now, what we want to be able to do is, understanding these characteristics, be able to tell whether a given situation calls for a linear model or an exponential model. So let's look at how we would compare those, okay? All right, so on page 782, number 6 deals with two different compensation plans for a job. So two different ways to calculate salary. So it says job A, okay, job A starts at $2,000 a month. And goes up by $300 each month. Okay? So, the first thing you want to ask yourself is, the increase or decrease, the change, is it additive or is it multiplicative? Are we adding something or are we multiplying by something? This will tell us whether it's an arithmetic progression or a geometric progression, whether it's a linear model or an exponential model. In this case, we start at $2,000 and we go up by $300. We're adding $300 each month. So it's an additive relationship. So we use a linear model, right? The change is constant over time. Whether we're at the beginning or we're 3 years in, it's going up by $300 every time, okay? So this one is, we recognize that it's a linear model. We're going to write a linear function to map this salary. So first we need our A and we need our B. We need our starting value and we need our incremental change. So our starting value A is $2,000, right? Our change B, it goes up by $300 each month. So we would say that the salary as a function of time is $2,000 plus $300 times T in months. Okay? $2,000 plus 300T. Okay? That's our function for the salary for job A. It's a linear equation. All right? Now, for job B, it says that it starts at $1,500 a month. Okay? And it goes up by 5% each month. Now here we see that even though something is being added, 5% is being added, that change that's being added each month is calculated using a multiplication problem. Because remember, percentage, we have to multiply by the previous value. So we have to say that 5% changes depending on what the previous month was. So we say, well, if it was $1,500 in the 1 month, right, 1% of that is $15. So 5% is $75. So in the first month, it goes up $75. But in the next month, it's going to go up by more than that because we're going to take $1,575 times 5%. It's going to go up by more. And so the change each month increases because 5% of your current salary grows as the salary grows. So it's a multiplicative relationship because in order to calculate percentage, we have to multiply. Okay? So we're multiplying by 1.05 each month, which I'll write that out to help you understand where that came from. So, but recognize that we want to write an exponential equation here because it's a geometric multiplicative relationship. Because we have the percentage, we need to multiply by the previous value. Okay? So our A, our starting value, is 1,500. Right? Now, our rate by which we go up is 5%, which is 0.05. Okay? But to get from 1 month to the next, we don't multiply by 0.05. Because if I, in month 1, made $1,500, I multiply that by 0.05. 1,500 times 0.05 is 75. I don't make $75 in the second month. I make 1,500 plus 75. So what I multiply by, the B, is 1 plus 0.05. And you should remember this from lesson 16.2. When we first talked about exponential models, we took that rate and added 1 to it to know what we multiplied by each time. Okay? So that means our b is 1.05. Okay? So to write our equation, it would be y equals a, 1500, times b, 1.05 to the t. Okay? So to calculate the salary in the 2nd, 3rd, 4th, 15th month, we would plug in the month number here for t, and the function would generate our salary. So this is salary as a function of time. Okay? So both of these are S of t. This is for job A. This is S of t for job B. And so those two things are related. All right? So what you're going to do is you're going to do some exercises where you have to do this. You'll have to state whether it's a linear or exponential relationship. You'll write the equation, and you'll say whether it's increasing or decreasing. Okay? So you'll want to notice things like if the situation it describes has things going down in an arithmetic way, this would be a minus, right? And then you would say that it's decreasing. Okay? Last note on comparing linear and exponential models, you won't have this in your exercises, but it's just something to be aware of, is that, like, for instance, in this case, right, if we put these on a graph, that 2,000 plus 300 a month would go something like this, okay? And the 1,500 plus 5% a month would go something like this. And so when we have an arithmetic progression, a linear model, it's going to start out going faster, rising faster than the exponential model. Okay? So this is increasing at a faster pace. This one kind of starts out flat. But eventually, because the rate of change of the exponential model increases over time, eventually it's going to shoot up and it's going to pass the linear model. So in general, like in this case, if you're comparing two compensation packages, you're going to see that the exponential one, the one that goes up by a percentage each month, is a better deal in the long term, right? But the additive, the arithmetic, the linear one, is consistent, but in the long term wouldn't get the salary as high. So eventually they cross and they flip which one is worth more or which one is higher, greater value. But again, we won't deal with that much, but it's just something to point out as we gather our understanding of linear and exponential models and how they're related. So again, you're going to do some exercises where you are presented with a situation. You say whether it's linear or exponential. You write the equation, and you say whether it's increasing or decreasing. Okay? So have fun with that. Happy mathing.